This talk will be, in a way, a sequel to yesterday, but I'll try to make it independent. So the idea will be to give you a very basic introduction to a very fundamental object in probability and in physics in general. And this object is called the Gaussian free field. And I'll try to just give you an impressionistic view of what type of things mathematicians have been recently discovering or understanding about this very classical object. Again, this is sort of, I will be quoting results by various people. I will not say each time who did what, except that I may just say immediately that most of what I will be saying is always joint work of Scott Sheffield plus somebody else. So he's sort of one of the central figures in this understanding of the geometry of the Gaussian free field. I'm sort of on one side of this, but just want to mention that immediately. So just as a very brief introduction, and it will be of a different type than yesterday, because yesterday I tried to show you that we're drawing things in a two-dimensional, in the plane, with your chalk or your pen, and try to draw something at random, trying to understand this. Now, what the idea that we have in general is sort of here, sort of more generic, that you can look at your favorite mathematical object and try to understand what it means to choose it at random. What is a typical something? So when we know how nice this is to look for a typical group, or a typical random group, random matrix, random whatever you have encountered in your math life, and it can be of interest. And it's not just, usually it doesn't tell you something about, how it's super fun, let's look at a random group, and it's not just an exotic question. It will be just also a question about, the generic structure or nature of certain of these objects, what they might be. However, so clearly the question of what do we mean by typical and how do we choose it, as we have seen yesterday, is clearly there are many variants of a similar question. But in this talk, I would just review very briefly what is a random function. Functions, one of the first things we learn in high school, and then what does it mean to choose a function at random? What does it look like? What can we say about random functions? And now then the next sequence would be, what is a random surface, or what would be a random membrane if you want, and what can we say about it? And just as a slight motivation to go slightly further, you don't see what is, but anyway, what is written there, down there, is what I say, so you can just listen. You might wonder, say, you're in the plane, right? And we all know how to measure distances between points in the plane. But then you wonder, you can imagine that you're doing little mistakes, right? That in your measurements, or that the true distances are actually not exactly Euclidean distance, but there's some, infinitesimal vibration away from it. And you want to understand that, right? So this idea of what would be the sort of natural, is there something like that that you can define? And it's going to be related conjecturally in some way to what I'm going to say. So let me just say just a couple of things, and this is just also that I'm going to list extremely classical things to start with, but in order to illustrate, it will be very useful, I think, to explain what happens in the more elaborate case of these random membranes. So if you're looking at a random one-dimensional interface, so you might say, interface between water and air, or something, ocean, but in a one-dimensional picture, then you just have a one-dimensional function that separates air from water. And the natural way you want to model it in a discrete world would be to use a random walk. And basically at each step you go up or down by tossing a coin. You do it 1 billion times. What picture do you see? Well, as we learn in high school, not in high school, but in sort of first probability courses, it's asymptotically flat. right? So what is a typical random function? What does it look like when you are not careful? Well, it's just the constant function. That's the typical random function, right? Because by the law of large numbers, you know, if you choose to go up or down with 50% chances, then on macroscopic scale, you are just flat. You have as many heads than tails. So what you want to do, however, is to say, well, you know, if you zoom in to this picture sufficiently, you know, you stretch the vertical direction enough until you see something, you will see something, of course. And what you see when you zoom in enough is basically a picture like this, which is what we like to call, I mean, which is more something getting pretty close to a Brownian motion. So this is a one-dimensional Brownian motion where the path goes up or down at random at each time, if you want. And you have done this infinite stretching in the vertical direction. So the way you should think of the Brownian motion, if you want, is the infinitesimal vibration away from this deterministic flat pattern of your random function, of your deterministic function. Okay, so that's one way to look at the Brownian motion. And in this way, when you look at the Brownian motion in this way, in some sense, you realize that certain features of the Brownian motion, like the fact that the Brownian motion can be viewed as a random Fourier series where the inputs, the coefficients in the Fourier series are actually independent Gaussian, this type of idea that is sort of the infinitesimal vibration away from the flat function becomes sort of more natural. Now, I just want to mention list a few things about Brownian motion that are going to be, that I would just want to remind you of. So the first one is that it's a Gaussian object. It has Gaussian random variables. It's a Gaussian random variables. And there's this funny thing about mathematics that, of course, Gauss is, you know, if you're a mathematician, Gauss is your hero, and he's our hero. Except that for 95% of the mathematicians, when you say Gaussian random variable, they see this thing with bell-shaped and say, you know, this is, I don't like that. You know, this is statistics or whatever, but it's still Gauss. You know, it's not, it's the same Gauss. You know, so it's nice maths. It's not about. And the nice thing about Gaussian random variable is that they are easy to define. So basically, in order to define a Gaussian process, in general, you just have to define the covariance structure. And in order to define the Brownian motion, it's one line. It's just a Gaussian process indexed by the real line, such that the covariance between Bs and Bt is T inf S dot. And that's the definition that's done. Okay? So Gaussian variable are our friends because they are variables that are easy to define and that are sort of come on very natural. The other thing is that there's a slight nasty thing that you discover in probability theory courses, either when you learn them or when you have to teach them, is that to prove that this Brownian motion is actually a continuous function is not a trivial fact. You have to work a little bit to check that indeed this object that you're defining in these two lines are actually defining really a continuous function. This is the blue curves that I defined you before. It's not difficult, but it's not a trivial fact. And in some sense, you should remember that why is it non-trivial? Because you have, you know, somehow you have stretched in the vertical directly with infinite magnification this infinitesimal fluctuation away from the real line, from the constant line, and therefore, you know, by this infinite stretching, you are doing something non-trivial. Now, again, as yesterday, this limit is independent of the microscopic model, so in the sense that you can take different type of random walks, you know, as long as there's a fair game. In large scale, you see always this microscopic model. In particular, there is one very nice discrete random walk, which you can define, which is just the following, is if you first draw a Brownian path, and then you look at the Brownian path at integer times, then basically the increments that you have at each step are themselves what we like to call Gaussian random variables. But it just means that inside the Brownian motion, you can exactly embed a particular discrete object that is sort of sum of Gaussian random variable, that would be a discrete object that is really naturally embedded in the Gaussian, in the continuous object. And it has, of course, a nice Markov property, which basically says the following, that is, of course, extremely elementary if you look at it from the perspective of the random walk, is imagine you define the Brownian motion up to time here. So the only information you have is everything that has happened before time t. How is it Brownian motion going to continue after that? Well, it's just going to be another sample of a Brownian motion that is going to start from here. Well, so that's the Markov property. Now, clearly, there is a scale invariance property because it's something that you have obtained as a scaling limit when you have zoomed in a certain way. So this guy is going to be a random fractal. And finally, I just want to mention one important object that's going to be relevant here, which is the object that we like to call the Brownian bridge. So imagine that you take a very long random walk, and you condition to be back at the origin after a long time n. And you look at the picture that you see by, and so typically you're going to see something that looks like a Brownian path, but it's sort of constrained to go back at the origin at time 1, say. This is what we like to call a Brownian bridge. And in some sense, it's the analog if you imagine that the Brownian motion itself after time 1, where you don't constrain it at the end, it looks like a bit of fluctuations of some rope that you hold at one end. And while the sort of, if you hold it at both ends, it will be sort of fluctuation of some sort of violin string. Okay, because they're attached at both ends. And now it has sort of an additional symmetry, sort of left-right symmetry in the picture, because you could look at it like this, or you could look at it like this. And the Brownian bridge is an object that is very easy to define in the continuum. And one way to define it, just would be to take just an open-ended Brownian motion up to time t, and then you draw this line that's just joining between 0 and t. And you subtract the pink from the yellow, and pink minus yellow is a curve that starts at 0, ends at 0. And this is what we like to call a Brownian bridge. So in particular, there is something going on in the continuum, which is only true in the continuum and not in the discrete case, which is that you could sample independently, first where I'm going, and then you sample the bridge, and then you add this bridge plus the linear part, and you get the Brownian motion. Okay, so there's something specific going on in the continuum that you do not see in the discrete case. Now, of course, in the Brownian bridge, there is something that you have the impression that the sort of Markov property is lost, right? Because there's no time direction. But it's not true, because imagine you condition on the Brownian bridge. You condition on the first part, you have discovered this is a Brownian bridge time 1, time duration 1. You have discovered the first part up to here. What is the law of what remains to be discovered in the remaining time, sort of between t and 1? So this has length 1 minus t now. Well, it's a random curve that has to join this point and this point in time 1 minus t. So one way to understand it is there's going to be the sum of this linear function and an appropriately rescaled Brownian bridge. So if you start discovering a Brownian bridge, what remains to be discovered is a Brownian bridge, and you just have to add this linear function. Okay, so there is Markov property, and you can also discover from here and from here, and what remains to be discovered in the middle is still a Brownian bridge. So all these are very elementary things that you learn in when you learn about Brownian motions. This is first type of things you learn about. So after having recalled this, I just want to go to the actual topic of the talk, which is try to define what would be our random mountain. So, of course, in some sense, this is a question everybody, we all thought about this. What would be the natural way to sample a mountain that we see as, shape of a mountain? Is this really random, or is it what sort of constraints are there on the cracks, on whatever that's going to create these mountains? And so clearly there are plenty of ways to proceed, but there are also very natural discrete ways to do it. Okay? And the natural discrete ways to do it would be to do the same as the random walk case. So remember the random walk was going up or down at each step by plus or minus 1. So one way to proceed would be to take, you take a plate, again, you're back in kindergarten. Your parents give you, you have to stay on this carpet, and they give you a bag with plenty of cubes that you're piling up on top of each other, and you're going to try to create a mountain. So basically, at each side of this carpet, so you have the carpet like this. Let's say it's squared, and then you look at a square grid, and on each of these square you put a little height, pile on some cubes. So basically, to each point on this height, you associated, each point here, z, you associate a height h of z. And the constraint now, of course, if you do it completely at random, you need some constraint. And the constraint might be, say, two neighboring points here, two neighboring z's, are not allowed to have a height difference larger than 1. Exactly in the random walk, two neighbors had to have a distance plus or minus 1. So this gives you plenty of possibilities to proceed to do it. And if you choose one of these guys at random, uniformly among all possibilities to draw your little skyscraper profile. This is a very well-known model called SOS model, solid on solid model in the physics literature, and it's the question. Then the question is, okay, if this thing becomes larger and larger, what do you see? And you can choose different models. You can say, well, let's instead of putting here, imposing plus or minus 1. Let's just say that two neighboring guys are, there's some spring that is sort of attaching these two guys together. So now you're looking at some like trampoline, right, with a web of plenty of strings, and then you're looking at trying to making oscillate. Clearly, two neighbors don't want to be, the string doesn't want to be too pulled out, so you're going to penalize sort of the configuration where two neighbors are too far apart. And in this way, you're going to construct a random discrete or mountain on some discrete world. And what you see at random is there a discrete continuous analog to the Brownian motion, the fluctuations of this thing? What can we say? So the first answer is yes. Everything that I said about Brownian motion will still work in the discrete case, in the continuous world. And so here I just say, this is just one way to define a discrete solid on solid model, but you can just penalize in a different way. So this is just repeating what I've just been saying. I just want to mention one important fact, which is that, again, there's this notion of boundary conditions that plays the analogous role of these Brownian bridge attaching on one end or the other end. So here you're looking somehow at the fluctuation. You have like a carpet, like a flying carpet, right? You can either attach it at one end by one corner, and then it's open-ended, a bit like the string, or you can attach it completely on all ends, like a trampoline or tambourine or whatever, and you have different variations. So in particular, you have different. You can also have your carpet that is attached on the boundary with a non-flat boundary condition. Maybe on the boundary you can have something that is tilted, or you have a tambourine, somebody walked on it, and then it's sort of a bit, the boundary is a bit tilted, and the question, and here of course you have more possible boundary conditions than you have there, because here the boundary was just, you have to fix the height here and the height there, but on the boundary of your carpet you have an entire function that you can choose. Now, again, if the boundary conditions are flat, clearly when the size of your system goes to infinity and you don't rescale things, you don't see anything, it's flat. It's obvious, it's much more difficult for a tent that is attached at every end to fluctuate than for just a one-dimensional rope. You're attached, you have much more constraint. And in fact, the oscillation in the vertical direction of this sort of attached tent would be much smaller than in the discrete case, in the one-dimensional case. So in the random walk case, it fluctuates like square root of n. And now here, this thing will fluctuate like square root of log n. So it's very, very small fluctuations. In particular, if you talk to an experimental physicist who knows about SOS model, he says, I know the SOS model. I see it in my experiments. It is really flat. It's 0. You can glide on it. What you're going to tell us here in a moment is nonsense. It's not physical, because square root of 10 to the power 26 is 5. Okay. So it's not like it's not true that the picture that I'm going to show you in a moment is just some fruit of your imagination in some sense. It's not quite true, but just one has to be careful here in the sort of validity of what is Gaussian stories here. However, it's asymptotically flat, but if you blow up in the vertical direction enough, you will see something. And well, what you see? Well, something called the Gaussian free field. So there is an object in the limit that captures the fluctuations away from the horizontal flat deterministic pattern, these random fluctuations away from this pattern. So I want to emphasize two things. The first thing, that embarrassingly, this is not known to be true. I think it's still an open question to prove this for this SOS model I described. So just to show you that even this analog of the central limit theorem in that particular simple case, the simplest possible case, the bag of tools is not quite good enough, and so it shows you that it's not such a trivial object to master, but for a number of other very natural models and a vast class of models, one can prove this. And I'm going to see that. So let's go through these properties of this Gaussian free field, just for to see what that basically everything we said about Brownian motion seems to go through. So the first thing is Gaussian. Of course, the name is Gaussian free field. So it's so if it's Gaussian, it's your friend, it's your nice guy. And actually, the way to define the Gaussian free field is to say, well, it's some sort of random gamma is some sort of random height, x. So d would be the shape, the domain you're playing it, the shape of the tambourine. And then gamma of x would be the height of the tambourine at position x. And it's just a Gaussian process where the covariance structure is given by the, what is the nicest function you can imagine well, it's the Green's function. So here, another of our heroes, Green, is here, and they come together in the Gaussian free field. Must be a nice guy, the Gaussian free field, obviously. Now, again, I told you there exists, a natural discrete approximation of the Brownian motion, that is the random walk with Gaussian increments. There's something like that we call the discrete Gaussian free field that you can view as projection of this continuous object in the discrete world. It satisfies a Markov property that I'm going to describe to you in a moment. It is very natural. And again, it's universal for various surface fluctuations, and you have papers by people, Deutschel, Giacomin, Sheffield, Miller, Kenyon, that show that this Gaussian free field fluctuation appear in a number of different settings. So it's really universal for a number of a scaling limit of number of discrete natural models. And there's a new feature. So the new feature, the good news is there's something more than the Brownian motion in one dimension. Namely, it satisfies a conformal invariance property. So what does the conformal invariance property of the Gaussian free field mean? So the conformal invariance property means the following. Imagine that you have a tambourine that is attached on the boundary with 0 boundary conditions. And you look at the fluctuation of this guy. Now, we know that it's possible to transform the disk into any other shape by Riemann's mapping theorem, as long as the shape in the arrival is simply connected. You can always distort your disk in an angle so that locally angles are preserved everywhere, as I explained yesterday, so that your pastry that you have here sort of gets mapped to this other place. Now, here, imagine that you are sampling this random mountain here. So the oscillations are in the direction here orthogonal to this thing. And now you stretch in this mountain, just in the direction of your blackboard, using Riemann's mapping theorem. But you keep this other coordinate that you have here fixed. Then in that way, you construct a random mountain that is attached to that has 0 height on the boundary, that has 0 height here. And the result is that the random mountains you get there is exactly the Gaussian free field with that boundary conditions over there. So that the random mountain with, that you define with 0 boundary conditions, say with in the disk, is basically the same type of object than the whatever boundary you take. So this is very nice. And now you just want to say one little word. Well, no, we'll come back to that a bit later about say that it's not so different than what we had in the one-dimensional case. But now I just want to say 2 words about the Markov property. Because the Markov property is something that is something extremely natural. What is the analog of the Markov property? Remember, in the one-dimensional case, it was you were discovering part of your curve, part of your rope, and you were asking, OK, I've discovered this part of the rope. What is the remaining stuff looking like? So what happens here is the following. Imagine here you have your random mountain. And you discover you have some explorers that sit on the boundary. Everywhere, here the boundary value is 0. And you tell them, OK, what do you need? You tell them, OK, explore everything here, the random mountain, all over the place here. OK, so you discover the height here in this annulus. And the question is, what is the law of what remains to be discovered in the inside? If you think about 1 second the discrete models, or this idea that what you're looking at is sort of the discrete counterpart of randomly fluctuating things, clearly the only relevant information that you need in order to understand what is in the inside is just the height of your mountains just on the boundary of what remains to be discovered. Okay? Because now what remains to be discovered is a mountain chosen at random among all possible ways that has exactly the right already discovered height on the boundary of this point here. Okay? Now, what is the law of what remains to be discovered there? Well, there's a first little, then we have to go back slightly here, because there's something I haven't told you. In the flat case, I've described you, OK, what's the natural, if I take a flat tambourine, nobody has stepped on it, asymptotically, the shape is flat. Imagine that now in fact, the boundary conditions, I go back, the boundary condition on the boundary of this tambourine is not flat, but it's sort of some function here. So it's something here like this. Well, what is the natural shape that the infinities, the stretched thing will want to take in order to, the deterministic shape that it wants to take? You think about it 2 seconds, and you realize, well, it will be the one. You think of these springs, attached to each other, and what is the function that is going to minimize the global energy of, all this set of springs that the surface is going to be choose? Well, it will be the harmonic function in the domain D with boundary conditions given by f. So f is the height on the boundary, and the natural optimal shape that your tambourine wants to take in there will be the harmonic function with in the domain D given with boundary conditions given by f. So it's another of our good friends in the solution of the Dirichlet problem that jumps in. And therefore, here it should not surprise you that what is going to happen, you have discovered part of this object here. You have discovered, therefore, a random something that you can view as the boundary, the height on the boundary of what remains to be discovered. What is the law of what remains to be discovered? The law will be the sum of this harmonic function that is it's a deterministic function of f, is interpolating in the inside the function f in the inside of what remains to be discovered, plus, well, the fluctuations away from that, which is a Gaussian free field in the remaining to be discovered domain. So you discover the Gaussian free field somewhere. What remains to be discovered is just a Gaussian free field with zero boundary condition plus the natural deterministic function that is going to be defined by the harmonic functions that, by the boundary condition that you've defined. And you go back to the one-dimensional case, and you realize, well, this is exactly what we've seen, because the Brownian bridge, I start discovering what remains to be discovered is the sum of the linear function plus the Brownian bridge. And the linear function are the one-dimensional harmonic functions. Okay, just the same. So it's exactly the same story here. There's a very natural Markov property in space. If you want to replace time by space, you can sort of discover things from here, from there, and then you have conditional distribution here. So clearly, you already see that in this Gaussian free field, what you will want to do is something like, OK, there's this random mountain to be discovered. And then you told your army that was on the boundary, you told all the soldiers, OK, explore everything until here, and then stop and tell me what you see. But you can also tell them, go and explore this mountain following certain rules. Right? Like try to always climb, or try to, and they will discover part of the mountain. The part of the mountain they discover depends on the mountain that they're discovering. But this type of argument saying, well, conditionally on the fact that they have discovered this, what remains to be discovered will be still a Gaussian free field with the boundary conditions given by what they have discovered so far. So the analogous role of what we like to call stopping time in stochastic calculus and so on, there is something like that that you want to define in this model. And it's really clearly obvious if you view this as scaling limit of discretely randomly chosen surfaces. Something. OK, so here we've gone through all these features. And I just want to mention one thing. The first thing is that here, how do you prove the conformal invariance? Conformal invariance is a one-line proof because it's just the fact that the Green's function is conformal invariant. So that's just one-line proof. So this is a very simple fact. Clearly, the Markov property is not completely as trivial, but actually it is. It's just a question, if you define it in terms of Gaussian Rennerville, it's just you have the L2 space of functions and you project into orthogonal subspaces, the one that have value 0 here. And OK, so it's just some very elementary features. So nothing here is difficult, except, of course, the proving that the discrete converges to the continuous. Now, there is some feature, of course, nothing here is new, and the Gaussian free field is sometimes called like the massless free field, or if you are learning quantum physics, quantum field theory, the Gaussian free field is just the most trivial thing you can think of. It's before even starting playing. This is sort of like this is the elementary cube that you want to play with when you try to do quantum field theory. So physicists know this thing since ages, and they have been playing with that, elaborating on this for a long, long time. Nothing new here. Now, the second important feature is that in that list, there's one thing missing compared to the Brownian motion. And the one thing missing is that I've been cheating on you all the time because I made, I pretended, and all your intuition that I tried to develop was based on the fact that it was actually a surface. And the bad news, it's not a random function. Gamma of x is not a function. So here we're in the case, when you take a random group or a large random group, it's a group. Or you take a large random function, it was Brownian motion, was a function. Now we take a large random surface, or what we thought was a random surface, it's not a surface. Right? That's basically the outcome. So that our ideology of what is a surface was not quite right. So what is gamma of x? Because everything here I said is right. So let me try to explain you what it is. Well, it's not a random function. And here, Kang, who maybe some of you have encountered here when he was at Caltech working with Nick during a couple of years. So he made a simulation. And so what do you see when you want to look at a picture of a Gaussian free field? Well, you see this porcupine like this. It has spikes all over the place in all directions. You don't see anything. It's like, and if you think about it, this picture is not surprising because remember, it was extremely flat, right? Square root of log n. So in order to see something, you have to blow up a lot in the vertical direction. And by blowing up until you see something, well, what you see is either you see nothing. As soon as you want to see something, bing, it's plus minus infinity both simultaneously. There's no way to capture it, So basically, this is the reason why in the physics literature, basically, immediately you say, well, this is not a geometric object. You can't draw things, or it's not a surface. So what you can do with that, and I'm going to say this in a moment, are things having to do with correlation functions or things like that. But it's not a random geometric object. So what is gamma of x? So the idea of what you can do with gamma of x is a generalized function. So by a random generalized function, I mean that if I have my domain D here, and I take an open set A, you can define the mean height of gamma on A. This is an object that is well defined. But the height at one point is not well defined. And this, I hope, will be very clear for you at the very end when I'll try to describe you, still some geometric insight into that object. And the reason for that, I'll just say a few words. The reason for that, of course, is that when you look at the expected value of gamma of x squared, what is the mean value of this thing? Formally, it's, in our definition, it's the Green's function x of x. And this one, we know the Green's function, by definition, it explodes on the diagonal. It's infinite. So gamma of x formally doesn't make any sense in, it's not a random Gaussian variable. However, you might try to say, what is the mean value of gamma on A? This will be the integral of dx gamma of x, where you are in A. Formally, you could try to define this thing. So you say gamma of A is this. So it's not the mean value. It's up to multiplication by the area of A. Now, if you take expected value of gamma of A squared, you apply Fubini's theorem, and then you get it's just the integral value of A cross A of dx dy g of xy. And you know that g of xy explodes very slowly when x gets close to y, and therefore when you integrate this out, this is finite. Therefore, the random variable gamma of A that you define formally as this one should have a finite variance and should be a Gaussian random variable with a finite variance. And so what are you doing? Well, we give up defining gamma of x. We just define gamma of A to be the Gaussian random variable with that variance, and which the covariance between gamma A and gamma B would be what we want it to be when you say A cross B. That's the definition. So you define as a family of Gaussian random variables for each open set A, you can define the random variable gamma of A, and the covariance structure is given by this. OK. So it's Gaussian. It has a discrete approximation. This is simple. Basically, you tile your domain into squares or triangles or whatever, and you take gamma in this triangle as the mean height in that triangle. Well, that would be a natural projection. Satisfies conformal invariance. Clearly, this definition is still, involves the Green's function, and therefore it inherits all these conformal invariance properties from the Green's function. It satisfies Markov property. So here, there's one thing I want to emphasize, which is that you can define the mean value on a set A, which is an open domain, but you can also take the mean value on a circle, for instance. Because log of, this explodes like log of the distance between x and y. So if in the one-dimensional space you integrate, log of 1 over x near x equal to 0, this still converges. So you can still make sense of the mean value of gamma on a circle, for instance. So how does the Markov property work? Well, we discover the Gaussian free field in this annulus. What remains to be discovered, we just said, is going to be the harmonic extension in the inside of the domain of what you have discovered on the circle, plus an independent Gaussian free field. So you say, well, this doesn't make sense because on the circle, it's not defined. It's not a function. It doesn't Well, it's still a generalized function. So for instance, what is the value of h in the middle? The value of h in the middle of this harmonic extension is the mean value of gamma on the circle. And the mean value of gamma of the circle is, I've just told you, it's well defined. You know, a harmonic extension is a mean value of the values on the boundary. So therefore, even though f on the boundary is not defined pointwise, the harmonic extension of f to the inside is well defined. So you see this feature that it's a very wild object, but here, when you start discovering here up to here, well, you discover it on the boundary, and then you have a harmonic function, h, in the inside. When you get closer to the boundary, it oscillates wilder and wilder. So it doesn't converge to a point on the boundary, but it's well defined. And this statement holds, that I discover the Gaussian free field in this annulus. I define the guy on the circle, all these possible meaned out value, and then I define the harmonic extension, and what remains to be discovered is just this harmonic function plus a Gaussian free field in this remaining to be discovered disk. And again, okay, it's universal for various surface fluctuation. Well, of course, the proof goes like what you want to. I want to emphasize just one little thing, which is, of course, that if you are there, you won't say, well, what can you say about the Gaussian free field? Well, you know that you can define something like this, even though it's not well defined. You can still make sense of this being the Green's function of xy. This doesn't make sense, but in some generalized sense, you can view this formula as being valid. And therefore, you can define things that look like what we like to call correlation functions, or in physics, where we say, the guy at x and the guy at y, they talk to each other and they interact in this or that way. It's a very natural thing to try to look at this type of features. Okay, any questions about this? No. Okay, wait a minute. I mean, this was just the deterministic Gaussian, and the different rules will come to there in a moment. I told this story for what's going to follow. This is sort of deterministic. When you tell to your guy on the boundary, you're going to explore that territory, they explore it, and then you. So clearly, how do you climb on the thing that is not the surface? It's hard to. Okay. Now, here comes sort of the new input, the sort of new vision of this Gaussian free field that sort of has emerged in the last years. In some sense, this was everything I said so far was like in the folklore and basic things. And as mathematicians, we learn about Brownian motion and so on. In the curriculum of a typical probabilist, you don't learn about the Gaussian free field because we have nothing to say about it. You can't study it. You can't look at it with a microscope. And therefore, it's not sort of it's very surprising. Very often you ask, what is the natural surface to a probabilist? They say, well, I know it's the Brownian sheet, which is another object. But it's not isotropic at all. It's not the natural random surface at all, the Brownian sheet. The Gaussian free field is the natural object, except it's not a surface. So we are sort of. So can you do something now? It's a random mountains, and we like to hike. We go to Lake Arrowhead or whatever, and we like to look at our topographic maps of our mountains. And the question is, can you define a topographic map of this thing, which is not a real mountain, but can you do something like that? And the answer, the message is yes. You can do something like that. So you can do something which is actually even better than in the real mountains. So this real wild world here is actually much nicer in terms of topographic maps. So here is a little story I'm going to tell you. So we have a way to construct at random in a disk a random picture of that type. Right? I'm not going to tell you how. I'm just telling you we have one way to sample at random an object like this. Why am I going to that direction? Imagine that you are here on the Gaussian free field with boundary value 0. Imagine that this is a real mountain, and you tell to everyone on your army to say, explore whatever you can without going higher than 10 or slower than -10. Well, so you try to walk around, and if this would be a nice topographic map, you would have the level lines at level plus or minus 10. They are sitting here. And you would be able to discover everything that is inside, in between them. And here, what remains to be discovered here is something that is attached to the boundary with boundary value plus 10 or minus 10. So the idea is try to do something like that for the Gaussian free field, because then you could apply the Markov property that saying that remains to be discovered here inside this loop of height plus 10 would be a Gaussian free field with boundary conditions plus 10. And then you could continue. So the idea, we try to invent something like that here, and then the idea is say, well, we have a way to construct some object that will play the role of these level lines of plus 10 or minus 10, the first level lines that you encounter. Now, clearly, because of what we had here, you would not expect this white area to have a positive Lebesgue measure, because you know that it's plus or minus infinity everywhere, so you will not be able to visit it, to get to some point here. You're not between minus 10 and 10. So the picture that you have going to find is more, Sierpinski carpet type, which is typically the loops that you are here. These black things are, have full Lebesgue measure. The white part, which is what you can invade in between, will have zero Lebesgue measure, but will still be connected. Okay, so it's a real random analog of this, except that as opposed to this picture here, our picture here is conformally invariant, so meaning that it's invariant on the group of Möbius transformations. So it really has this hyperbolic picture. So we have a way to construct at random a picture like this, which is a random fractal where the Lebesgue measure of the white part is 0, but you construct it like this. Now, we sample this guy. Here it is. And for each of the loops, we're going to toss a coin independently to decide if it's actually plus 10 or minus 10. That's the idea. So independently, you toss a coin. So now, what you want to do is, well, if that's the level line of plus 10 and I've explored it from outside, I can say what remains to be discovered. I want to do the same thing inside. Well, I can do it because I can use conformal invariance. My way to sample these loops was conformal invariant. So I repeat the experiment here by taking a conformal image of this random way of choosing a family of loops inside there and map it in there. And you do this a second time. And then you toss a coin again. So what would be the height of this guy inside these two loops? Well, here it goes up by 1 and by 10, and up the second one by 10, so it's plus 20. This one would be up 1 and down 1 would be 0. Right? So in this way, what you define is a function, a random function, that is defined, has value minus 20, 0, or 20, everywhere up to a Lebesgue measure set of points, a set of points of Lebesgue measure 0. So in particular, you can define, I take any open set here, I can define the mean height of my collection of podiums, because the mean height, you don't care about the set of points of Lebesgue measure 0. And you iterate. Okay? You do it 3 times. Inside each loop, you continue. So that way, you construct a function, hn. After n step, I have a function n, which belongs to basically minus n times 10 and plus n times 10 in this way. OK, so you have these random plateaus. Now, what the claim is the following, is that when you do define for each a, you can define hn of a, which would be the integral over a of hn of x. Well, you can define the mean height. After n iteration, you define the mean height of what you see. If you try to let n go to infinity, because the loops become smaller and smaller, the effect of the fluctuations is going to be smaller and smaller, because you have by adding all these little loops, it will be the sum of plenty of coin tosses, which is very close to 0. So it should not surprise you that when n goes to infinity, hn of a is going to converge to something. Almost surely, Hn of A is going, the mean height of this picture after n steps is going to, for a given set A, it's going to converge to something. And the object it converges to is now going to be continuous random variable because it's not, you're integrating this over the area. So it's the mean value of stuff that is in between. So let us just want to mention one thing. What is the height above one point? After first iteration, because this point is with probability 0 in the white part, it will be surrounded by a loop with probability 100%. And therefore, the height at this point is going to be either plus or minus 1 coin toss. After 2 iterations, it will be surrounded by 2 loops with probability 100%. And you go on like this. So what is the height Hn of this point after n step? Is the sum of n coin tosses. So Hn of x, when n goes to infinity, x fixed, this is just, when n goes to infinity, it doesn't converge. It's just the sum of IID, of a sum of coin tosses doesn't converge. However, Hn of A converges. So of course, now you can guess to what it converges to. The family of all these random variables Hn of A, when n goes to infinity, converges to the Gaussian free field itself. So what does this tell you? This tells you that in some sense, the picture that we have described here with these loops is really the topographic map of this Gaussian free field. You can really view it as this is the first level line at height plus 10 or minus 10, and I can discover it from outside, and then I iterate in the inside, and I get exactly this. Okay? So instead of saying the Gaussian free field is this porcupine, we don't understand anything, you can say, but the Gaussian free field is this family of all these nested loops, one oriented loop, say, either going up or down, and that's the Gaussian free field. It's there. And you say, well, but that's not true. When I bike up my pass, I have my map with plus minus 10 things. There is life. There are a little fluctuation between minus 10 and 10. Sometimes you go up and then you go down a little bit, and then it goes up 5 meters. And you say, no, I don't want to climb anymore, but it's because you are somewhere in between 2 level lines. It wasn't on the map. Here, you don't care about what is in between the lines because the white thing has Lebesgue measure 0. And therefore, it's not relevant to know what the height is in between minus 10 and plus 10 because you don't need it to define the mean height on an open set. So you have this discrete looking function. And this discrete looking function with level lines plus or minus 10 is actually the Gaussian free field. Because you only view it as the mean value on the type function. Now, there are 2 things. The first thing I want to emphasize is that this plus 10 I've been using here has to be chosen in a very good way. It's just one particular value of plus 10, if you want, that works for this, so that this works. Okay? So you will not, you have to, these steps that you have here, these podiums, have to have exactly a well-chosen height. And of course, in order to choose it, you have to choose what normalization you use for the Green's function. And no 2 mathematicians I know have the same normalization, 2 over pi, 1 over pi, blah, blah, So, but basically, there's a natural h which involves some square root of pi, because of course, square root of thing squared is going to have to cancel the 1 over pi. Anyway, so there's going to be square root of pi over 8 or something like that you have to use here. And if you do it in this way, you converge to that function. That's one point I want to say. The other one is that these lines are not really level lines. They are really cliffs. Why is that? Because you say that this guy here, in the inside, you can say it has height plus 10, say. That's correct. What is the height on the other side? Well, the height on the other side, you have plenty of small loops nearby, and each of these small loops, some of them have a height plus 10, and some have height minus 10. Half of them have plus 10, half of them are minus 10, so therefore the mean height on the outside is 0, if you want. So therefore, you should really view these lines that appear here as random cracks, random cliffs. They are not level lines, they are cliffs. So it's the derivative, if you want, of the Gaussian free field in that direction. That makes. Here, in the statement I made, is that the topography you define, right, these level lines, are defining for you the function gamma, the Gaussian free field. I said Hn converges to the Gaussian free field. That's fine. Now, what you can do, and this is a difficult statement, which says that if I give you the Gaussian free field, don't worry, I'm telling you what to do. If I give you the Gaussian free field, there's just one topographic map that works. The topographic map is actually a function of this generalized mountain. And this is a very subtle, here I say, I first define the topographic map, and I reconstruct the Gaussian free field that corresponds to it. Here what you have is that if I give you a Gaussian free field, you can recover this topographic map. So therefore, it's really something like you have this thing, and you send your army to the inside, and it discovers the lines in a deterministic way once the mountain is defined. This is a tricky result. Now, I just want to mention, once you have this now intuition, I want to mention certain research lines that are related to what I've just told you. So in some sense, the new input that sort of came is that Gaussian free field has a geometry. It's not just an abstract generalized function that has no geometric meaning. It's actually very rich when you want a very rich mountain that you can travel on and do stuff. So you can try to define, using the Gaussian free field, things that are going to be good candidates to define random metrics or random distances. So for instance, you can say a Gaussian free field, each time you go up a factor of level line, petrol costs twice more to travel in. And if each time you go down, petrol costs, you have a bargain of 25%. Okay. Now, then you say, well, what's the shortest path that goes from here to there that I'm using as less petrol as possible? Well, this is going to be a way to define me some sort of distance in my domain, and this is supposedly, related to what physicists like to call Liouville quantum gravity. Now, there are questions that relate this conjectural metrics structure to discrete objects that I mentioned briefly yesterday. I'm not going to elaborate on that, so that there are discrete random metric spaces that's supposed to be related to that. There's a link with random weldings, and here we also have some Kari and have been also top experts on that in this room, in this conference. Eero, Kari, well, anyway, and Nick, and anyway, it's a bit embarrassing to say that. To mention that I mentioned that because I barely understand this stuff. Of course, behind the scene, which I haven't told you, is that there are the SLE process that I introduced yesterday, because these boundaries, these level lines that you see here, right? These boundaries of these, these cliffs are actually variants of these stochastic Löwen evolutions. There are these fractal, one of those, they are fractal with dimension 3/2. They are fractal curves, that almost touch each other but are simple and are one of these variants. Except that here you have to define them all together, all these interacting loops, if you want, that all interact with each other. Now you can do other things and try to define on this Gaussian, on this random mountains, other objects. You can tell, instead of saying try to define the random level lines, you say put someone with skis on the mountain, and the left ski is smaller than the right one, and therefore it always tends to turn in one direction. And it will sort of follow certain, instead of going straight, that would be if one ski is infinitely longer than the other, it will start to sort of glide down, but therefore always turn in one direction. And these type of things can be defined and define other SLE curves inside a topographic map. It's sort of a natural thing to do, technically difficult to actually work out. But now, then you can do all sorts of other things. Now, in this fractal set, for instance, you know what the fractal dimension is of this wide part here. You can compute it, which typically you can never, the type of thing you can never compute if you are taking a random Cantor set or something like that. This is not something you can get, what is the dimension of the remaining component to component. And then you can try to do, well, let's do analysis in this random carpet. And what can you say? And basically, you can do all sorts of try to do all sorts of things. You can do, the first thing is, of course, there are other carpets. There's a one-dimensional family of carpets that you can play with. And you can, because of conformal invariance, what you can try to say is, can you, for instance, like what Stefan and Brent Werner have been doing, is sort of, can you define the generalization of Mario's uniformization theorem for Sierpinski carpet? Can you say that this is conformally equivalent, this set with holes is conformally equivalent to a circle domain? Conformally in the appropriate sense. Then you could try to say, well, is it possible to find something like Laplacian or Brownian motion in this carpet? Can you define random structures in this carpet? And what happens is that because of the fact that this is these are very special random structures, there are a number of things that are not accessible via, when you look at the standard random fractal, that are actually accessible here because you have conformal invariance with you. You have this flexibility of the fact that the holes, you discover one hole, what remains to be discovered is still more or less the same because of conformal invariance in distribution. So it's much more flexible than the usual random fractals. And so there's, exploding sort of possible, each one, imagination can, produce different ways, and there are a number of, things that you can do in this direction. What we've been doing recently with Jason Miller is basically understanding what critical percolation inside the carpet actually is. And there's an interesting feature that shows up, is that of this duality between SLE, different SLEs, that says that you can very well understand what critical percolation would be if you try to sample it in this random carpet and try to do these things. So of course, in that particular one, it's not so interesting, but in the others, when the carpets are a bit more sparse, then you can actually describe exactly, you have very surprising features that show up and that enable you to say certain things. For instance, for those of you who know the story, if you explore these loops one after the other by attaching these, you have a tree and you have these leaves that grow from this tree in a natural way, the trunk of the tree will be actually an SLE 16 over kappa if the loops are SLE kappa. So this is just one story. Maybe I'll tell more about it for aficionados that go to Lake Arrowhead, I don't know. Anyway, so the outcome is that the Gaussian free field is a super nice, natural, fun object because it's Gauss plus Green plus Riemann plus everything you want, and therefore it has to be a nice object. It should be related to all sorts of nice things. And indeed, you can do plenty of nice stuff on it. And this stuff is going to give rise, because of this very rich structure, to all sorts of natural and nice mathematical. You can relate it to other parts of mathematics in different ways. And depending on your taste, you can find aspects of it that you will like and can play with. That's basically everything I wanted to tell you, so I thank you for your attention.